Alright, check on this.
Alright, so this is problem. Everybody can see this?
Yes.
Kepler's third law. This is second law. You start with second law. Okay? The second law says equal areas traced in equal times. And this is the story for the left hand side. H is constant. Equal areas in equal time. dA by dt is constant. Okay? See, this is something you should understand. You should make a habit of understanding why this is second law. Not a habit, but just put your thought into why this says that statement is second. And this is the third law. Okay? The time period of an orbit is proportional to the semi-major axis. So there are semi-major and semi-minor. This is semi-major axis. So this is A is the representative of mean distance from the central body to the orbiting body. For an ellipse, it happens to be the semi-major axis. For circle, what is this?
The radius.
That's the radius. So that is the reason we have
That's
R.
why it was R. Okay, I see.
So that's the reason we have R for circle. So for circle, you will see T is equal to T2 pi over mu into R. So when you are doing this, what I want you to understand is how to get this for this derivation. You don't worry about it. Start here. But if you are asked to derive this itself, can you do it?
So we should be different by that equation.
You start with dA equal to area of triangle. Okay. It is M1, M2, V. So in this point is M1, this point is M2, and let's say this point is V. Okay. So what you have is if you have an ellipse, what you're trying to do here is, this is what makes it interesting. You have an ellipse. This is where M1 is. This is where M2 is. Okay, and we are talking about. We want to get an expression for. So what we said was, if you take, if this is dA1, this is dA2, and both these, so dA1 over dt is the same. If the time taken, equal areas will be traced in equal times. That's what we are trying to prove. So what we do is we assume that for a very small portion of the circumference, this becomes a triangle. If the circumference is really, if you consider dA, which is very small, infinitesimally small, it becomes a triangle. And what is dA is simply the area of that triangle. And what is the area of the triangle? Half base into height. We all know that, right? Everybody knows that, half base into height. So this is half base into height. Okay? Half base is this. So base is this.
Which is our V.
It's actually V dt. V is the velocity.
For the time.
Yeah, velocity. So velocity is in this direction. dt would be what?
Perpendicular to the R.
dt is just a time difference. Time taken from this point to this point. It's the time. If you multiply velocity by time, what are you going to get?
Distance.
You get distance. So dv into dt is this distance. You get it?
Yeah. DT, you said time taken from what point to what point?
From this point to this point. From this point to this point. Okay? time taken from that point to that point. So it is simply v into dt, right? And the height is, how do you calculate the height? Height is always, you look at this base, okay? If this is your triangle, what is the area of this triangle? Base times height. So you can say if this is base, half base times height, right? This is always the height. Height is the vertical difference between the base and the vertex. So you can actually do even this as the base. This as the base. In that case, this would be your height. Got it? So you'll get the exact same answer whether you take this as the base, this as the base. As long as you the corresponding height, if you take it, you're going to get the same area. Got it? So here it is. This is the height. Okay.
So this one right here, though, that you just drew, you're saying that the height is the little line in the triangle?
If this is the base,
Oh, okay.
this is the height.
Okay.
If this is the base, this is the height. If this is the base, perpendicular to this, perpendicular to the base is always the height. Got it? So you can consider any side of the triangle as a base. The perpendicular erected is the height. So you can do that. If you do that, you're going to get this. Now there is an angle here. You can see it in the textbook. The angle phi, it actually has a significance. I'll show it to you here. Alright. Let's just say we know that angle. Okay. So that angle is this angle. Okay. This angle is named as phi because this angle is that phi. Actually, the definition is this angle. So it is vertically opposite. You understand those parallelogram laws, right? This is phi, this is also phi. And if this is phi, this would be, since this is r, this would be r sine phi. Opposite. Okay? So this is r sine phi. So you're going to get half v dt into r sine.
Isn't this number 3, not number 1?
This is not number 1 or number. This is just I'm explaining to you how to get this.
So you just divide the dt to the other side to get the.
Yes. So V r sine phi is h. It happens to be. So you have this thing, right? So dA over dt. From this, what you're going to get is dA over dt is equal to 1/2 V r sine phi. And it happens to be that this term is h. So dA over dt is simply half.
So is H that long line connecting M1 and V? Is that H?
No, h is angular momentum. Angular momentum is what? R cross V, right? And R cross V is, it will be R, magnitude of V plus angle between
The two.
R and V. So you see angle is between R and V.
Oh, okay.
This V is angle between R and V.
Okay.
You see it? This is the R direction, right? This is the V direction. And this is the angle. So it is R. If you take the cross product, what is the cross product? Magnitude of R, magnitude of V into sine of the angle between R and V. Sine of angle between R and V is phi. Right? That is what you get. V R sine phi is H. You have to only understand that this here H is R, okay, V sine T, an angle perpendicular to R and V, right? This is a vector, so the direction has to be perpendicular to R cross V. If you want this, the angle doesn't matter.
If you what?
If you want scalar, the angle doesn't matter. Because this is always a unit vector. Unit vector R cross V. Okay, this H is always unit, this is unit vector. Because the magnitude is captured in this. So if you want this becomes, so you have, this is R V sine T. And R V sine Phi is H. That's how it will be. So what you do is, you start with H, okay, and go through the derivation. Can you do it? Second one is fairly simple. What is the second one?
Starting with the 2 by problem, you gotta find Kepler's first law.
Kepler's first law. So orbit equation, right? So that is the orbit equation, trajectory equation. So you start with, again, refer the road map. Road map, yeah.
Oh, yeah.
That is important. I think I've told you that.
In the top right corner.
Better?
That's fine. Do it fine, so.
Is it good?
Yes.
Everybody can see. Alright, if you look over there, what you see here is, I will always ask you to start here. Okay? Not always, but there are, we discussed 3 types of constants in this thing. And the first one is conservation of angular momentum. That is this. This is a definition, but you can also prove that R cross R dot is constant, or d over dt of R cross R dot is 0. We have done that in your assignment, and it's one of the questions. Now what you're trying to do is, you're starting here and you're trying to get here. This is the orbit equation. You can actually keep a copy of this if you want for your exam. You can maintain a copy. Will it help?
What? Which one is that?
It's appendix B.
It's appendix B. Yeah.
I think it's which one is 10%?
Hmm?
Which one is 10%?
Whatever you want, whatever is decided in the assignment, in the syllabus. Okay, so you have to get from here to here, from this point to this point.
Well, isn't that like a?
Why is this Kepler's first law? What is Kepler's first law?
Kepler's first law
Thomas, you have
All orbits
That's in the book.
all orbits move into
Huh?
the sun.
Huh?
All orbits move with respect to the sun.
All planets
all
move
orbits
in
move in
elliptical
elliptical
orbits.
Oh, okay.
in ellipses. So why is this? What does this say?
What do you mean?
Says that.
What does this again? What is? How do you say it in English? What the?
So R
Hmm.
is the distance is equal to the square of the angular momentum.
No.
No?
See, you cannot just say word by word. You cannot. There is.
Are you talking about
Don't-
just the
So
orbit
the
formula?
distance of the orbiting body to the central body is going to be found into that equation because R is always changing based on where it's at in orbit.
How does it relate? How does it relate to Kepler's first law?
The orbit formula, how does that relate?
Yeah, I told you guys that this is also the equation of a conic section.
Oh, yeah.
If you just flip back your you won't probably it was mentioned in the notes as well. This is also the equation of a conic section. What does that mean?
That means
The,
See, what it means is R can trace the trajectory of a conic section. What are the conic sections we study?
circles,
Circle, ellipses, hyperbolas, and parabolas. These are the four known conic sections.
R can chase the
R
what?
can trace any of the conic sections. It is exactly the same as if you're studying geometry, if you're studying conic sections. Huh? So that's what it says. An ellipse is a conic section. Right? So that's what it says. Kepler's first law. So R is the trajectory. Orbit equation. R is the trajectory. Here, H is constant, mu is constant, E is constant, R is only a function of that theta.
But I'm trying to put it into words in my mind. So you're saying that R is the trajectory, and that the equation that R is equal to is for conic sections.
This equation of this expression you are seeing is one. It is the orbit equation in the context of space mechanics, in the context of orbital mechanics. But in the context of geometry, it is the equation of a conic section. It is exactly the same. The equation of conic section and the equation of an orbit are the same. Okay?
So is that the explanation for how that relates to Kepler's first law?
So Kepler's first law says the trajectory is an ellipse. Does it matter how big or how small the ellipse is? An ellipse is always an ellipse. Okay? So even if the trajectory is a big ellipse around the sun, it is still an ellipse. Whether you draw an ellipse or whether you draw a big ellipse, it's still an ellipse. So it happens that it's always in the same plane. So there are two stages to this. One is you cross it with H. Okay. The first stage is you cross it with H. Look at your notes. We have derived this in your notes. Cross with H. And then stage 2, you dot with R. So here, expressed as derivative. So you express as derivative, then you take the derivative out, you say that is constant, and you dot with H, you divide by mu, then you say that constant over mu is E. look it up. It's actually, this is probably the lengthiest derivative. Okay. What is the third one?
I think you did.
That's what you did the third one.
Okay.
You did-
I did the third one.
Yeah.
Thank you. I'm sorry. What is the fourth one? So this is the third one. Okay.
That one.
The fourth one, explain why the radial component of the angular velocity does not contribute to the angular momentum,
Right.
using that one expression.
Right. So this is something you need to again practice. Okay. See, because motion of an orbiting body is limited to a plane, both the position and velocity vector will always have only two components. So what you have is, you have H, okay? You have R cross B, right? You have R or R UR cross with B R UR plus B perpendicular. This is the mathematical explanation as to why only tangential component contributes to the angular velocity. What you have is R UR cross with VR UR. R UR cross with B perpendicular. This is 0 because vector cross with itself is 0. This is how you are going to express this. R, V, R, U, R cross with U, R. You see, its vector cross with itself is 0 plus R B perpendicular UR cross with. This will be in the. So look it up here. This is a velocity, right? So this velocity will have two components. One component is this VR, which is in the R direction. And the other component is tangential to this or perpendicular to this. Perpendicular to this. This is that V perpendicular. Okay? So you have this. That is the reason we say radial component does not contribute to angular momentum.
This course helps if you don't want to go to the
Huh?
Does this course help if you don't want to go to study astronomy?
We are not studying astronomy. Astronomy is something different. See, don't get dejected.
Where do you apply this?
Hmm?
Where do you apply this in aerospace?
You are applying it. See, because you are applying this, because somebody studied this, somebody took the pains to study this. You are sitting here. You are sitting in the aerospace department. Aerospace, none of the aerospace would be possible without this. Even aircraft would be possible without this. So, I understand the frustration, but don't give up.
So the problems that we see on homework 3 are what we can expect for the test.
You can expect a little bit twist here and there, but you can expect the same.
You said a little what?
A little twist.
A little quiz?
Twist.
Twist. Oh,
You can expect.
Open book, open notes, right?
Huh? If you want open book.
I don't know.
That's not a trick question.
Let's do like one.
If you want open book, then you have to be prepared a little more.
What does that mean?
So
that
open
ain't
book
gonna come
is,
directly from the-
you may sit there, you may go through the book 100 times, you may not be able to figure out what that is.
Yes.
Was the book
It'll not be direct. Like you will not be given, search where it and then copy it and give it to me. That kind of problems will not be given if it's open book. Open book is applying. So I'll twist the problem significantly if it is open book. Either way.
The same thing. So basically we're doing a lot of deriving of these formulas.
Well, I'll give you problems as well. Just substitute and
To substitute
numericals.
what we
Yeah.
get into the problem.
I use open book.
You want to do open book?
No,
No. So are there problems in the book that are examples of problems that we can do on the test? Because most of the homework is just deriving, so are there problems that we can use to prepare for the test?
Yes, I'll do one thing. I'll just go back now and then give you a few numericals as well.
I think
Okay.
tomorrow
Make sure-
we can like go through some few numerical problems.
Yeah,
Yeah.
that makes sense.
Because we're going all these variables and then
I have to go through the material as well.
But so then when are we gonna have time to do the numerical values?
Numerical is actually simple.
But-
So you guys
You
start
just have to
practicing.
substitute.
Well, so when are we gonna
See,
do it with him?
You have to just know how to see. We did some numericals, right? Where you substitute mu.
like if we see the problem,
but-
the numerical value, then we can like more visualize it. When we did variable, we can visualize it. That's no problem.
So this is a derivation.
Yeah. So
One with
Some of the
numbers, one
variables.
with numbers, a problem with numbers.
yeah.
All of this is not going to be numbers. So I have given you numbers even in this homework. You realize that?
So you mean like the one,
Which one is it? Oh, okay, I didn't get to the back page yet.
The back page, there's a big numerical in
Okay,
there.
I see it. Okay.
so
So
those are the type of numbers.
This class will be like 6 credit hours.
see, I'll tell you, don't worry. Just go through this as much as possible. It's worth the pain. Okay? Alright. So this is, I'm willing to help you and take this help. There are very few, if you go outside of this, there are very few people who can actually help you in this, particularly in this course, and especially as aerospace engineers. You're all aerospace engineers. You are expected to know this.
I'm gonna know this on the master's by tomorrow.
Huh?
We'll have it by midterm.
Alright, so next one. So this is the mathematical explanation. The simple explanation is F is, you have to relate force, linear momentum, torque, angular momentum. Change in angular momentum will result in torque. Change in linear momentum will result in force. Right? You know that?
Yes.
That's what law is that? Change in linear momentum results in force.
That's the first losing law. Fourth one, the second one.
Second, F is equal to ma. That is, this is the exact, H is, so d over dt of H will result in torque. D over dt of, what is the linear momentum? If we use L, force.
What's L?
Linear momentum. So you have d over dt, right? This is, what is this? M, B is equal to F. So we assume M is constant, that's the reason we have M is equal to F. This is Newton's second law. So similarly you have d over dt of R cross mv is equal to T. So you have d over dt of R cross mv is equal to F. So we assume M is constant, that's the reason we have M is equal to F. So we assume M is constant, that's the reason we have M is equal to F. So similarly you have d over dt of R cross mv is equal to T. So you have d over dt of R cross mv is equal to F. So we assume M is constant, that's the reason we have M is equal to F. Okay. This is what is this? This is angular momentum. This is h. This is this is h, capital H, not small h. H is specific angular momentum. This is simply x. So this angular momentum, to induce angular momentum, you always need a moment arm. Okay? If you apply, what results in translational motion? When the applied force is acting to the center of mass or the center of gravity, that force results in linear momentum, a change in linear momentum. If I push this cart and my force goes through the center of gravity or center of mass of this, it results in linear motion. If I push it like this, it results in angular momentum. So when I say velocity, my velocity is somewhere like this, okay? There's a component like this, there's a component like this. This component, so if velocity is this, okay, this component is a radial component. Regardless of how much I push in this component, it will not give any angular momentum. Only this component will give you that angular momentum. Got it? So that is the reason, that is a physical explanation. So this is the mathematics. What is the fifth one?
The fifth one is through substitution of the relationship.
Right. So that is again it's simple but it's tricky. So H is equal to RA VA or H is equal to RP VP. Okay. You just start with, this Vis-Viva equation. Go back to, you have this handy. You can see the Vis-Viva equation here. Okay. Conservation of mechanical energy, total mechanical energy. Okay. E is V square over 2 minus mu over R. So from this, you can either use this or you can use this. This is V square is H square over RA square over 2 minus mu over RA square, RA. Okay. Now you have to, RP is A into 1 minus E and RA is A into 1 plus E. You should know this as well. Okay. So if you substitute that, you have H square divided by A square into 1 plus E square divided by 2 minus mu over A into 1 plus. Okay. And you have to substitute for H as well. H is A into root of 1 minus E.
So H has a different value than the what you got circled there. And you said you gotta plug H, you gotta substitute H2, and you're saying that H has another value besides the ones that you have circled.
Right.
You said, so when we plug back in, we can't plug back in what you have circled. That's not gonna get us to the final answer.
You have to see, you have to get rid of everything. The final answer is minus mu over 2A. Okay. I'll try to give you as much information as possible. If something is missing, you can ask me in the exam and I'll give you that information as well.
So how long are you going to be in the office on Wednesday? How long are you going to be in the office on Wednesday? Like afternoon?
I'll be there at least until 5.
6 o'clock.
Huh?
6 o'clock.
You have H's. See, all this you can actually just compute yourself. If you know from there, what is theta for RP? At P, what is theta?
P is over here, right? So is it,
So there.
So,
so
what is
it's,
stated? 0?
I don't understand the question. What, you said,
And P, what is stated? P is a petty abscess. The closest distance from the central body.
Theta is 0. If you have theta 0, you have R is h square over mu.
if theta is 0, you have one more time, oh, no, if theta is 0, you have what?
A squared over mu.
Thank you. So you're looking back at the orbit.
So you have h is actually
Oh,
square minus 1.
and you derive that from what you just wrote for H, you derive that from what? Again?
I'll just give you this information. So I can derive that way for you, but let's not complicate. So I'll give you this information. You have to substitute that here and figure out the answer.
so the final answer goes to be.
So if you do that, you're going to get. Use all of this information to practice this and try to arrive at the answer. Okay? What is the sixth one?
What happens to the a squared?
Hmm?
Oh, you
So a square, you substitute a square into e square minus 1 square. E square minus 1 is what? 1 plus e, 1 minus e. 1 plus e cancels out. 1 plus e cancels out there. You have,
Oh, I see.
right?
Yeah,
So that's how you get the.
at the one H.
You have to just replace h. You get it. What is the sixth one?
That's the escape.
V escape. Okay. V escape is actually a very beautiful concept again. So what you have is the escape velocity is always associated with parabolic orbit. Okay. What does escape velocity mean?
Velocity is over exit over.
Exit, not orbit. What does it mean?
Gravitational.
Gravitational pull. Okay. So you have to remember this. You have circle or ellipse. Okay. Parabola. Hyperbola. We have E and epsilon. E is either 0 or This table you have to keep in mind. Okay. Again, you can derive this. There is nothing that you cannot derive. So what it means is energy, total mechanical energy of a closed orbit is negative, which means it will never have enough energy to escape the gravitational pull. Okay. If it has enough energy to escape the gravitational pull, but not do anything beyond that, it means it will go into a parabolic orbit. It will escape the gravitational pull. Okay? But that's it. It will not do anything beyond that. That means the energy is zero. Okay? This is just eccentricity value. Eccentricity is 0 for circle. It is between 0 and 1 for ellipse. Eccentricity is 1 for a parabola. The eccentricity is greater than 1 for a hyperbola. But the energy is positive or greater than 0, which means it escapes and it keeps going. There is still some energy left to keep going. Okay, that is beyond escape velocity. This is beyond escape velocity. This is exactly escape velocity. You see it? This is precisely or exactly escape velocity. It is just enough to escape the gravitational pull. Got it? So if I use this equation, if I apply this to a parabolic orbit, right, I'm going to get v square over 2 minus, so this is 6 points, mu over r is equal to what? 0. So what you're going to get is v is 2 mu over r, right? Or v is square root of 2 mu over r. Okay. And we have already proved that v circular. What is v circular?
You have
Square root of mu over r. Okay. Can we prove that?
Yes.
How did we prove that?
With the h equals r times v perpendicular, you can start there. For v circular? Yeah.
Is that where we start?
Mhm.
Sure.
Yeah, so h equals r v perpendicular, and then we plug that value for h into the r equation.
Okay. So you're what?
Into the orbital equation, because e was 0.
Right.
Yeah.
See, it so happens, for a circular orbit, v is v perpendicular. The velocity is always perpendicular. Okay? So you can say for v, for a circular orbit, v is simply v perpendicular. Try to draw one circle. So everywhere it's always perpendicular. Both the radial and the perpendicular components are in that only. Okay? It so happens that for ellipse, see, you have to understand this. How do we get this RAVA? Here, the the velocity is perpendicular. V is V perpendicular. Here velocity is again V is V perpendicular. There is no radial component there. And these at the apoapsis and periapsis, there is no radial component. The radial component and the perpendicular component are both in the perpendicular component.
What is that you just drew? What's the connection to that to the H equals?
This is so what happens is since V is V perpendicular always, you can say H is VR for circular. Okay, this is sine omega, right? Sine phi, right? Phi is 90 for circular orbits. The angle between the velocity and this thing is 90. Okay, so this becomes 1. This is just VR for circular orbits. So it so happens that if you substitute this in r equal to a square over mu 1 plus e cosine theta. Okay, we're going to get again this is
For the circular, V is equal to 0.
right.
So
This becomes a square over mu. Okay, so you have a square is v r, v square r square over mu. Okay, and r. Then you have r. V is square root of mu over. So for V circular. Okay, so if we have derived this again, root 2 into root of mu over r, which is root 2 into
So the H though, when you say H circular equals V, that's V perpendicular.
no, V is V perpendicular for circular orbit.
Right.
In circular orbit, there is no radial component. All the velocity required to keep going and to escape the gravitational attraction is in the V perpendicular. That is only one component.
How did you go from this V circular up to that point up there?
So this is strictly for escape velocity. Okay. This you understand?
Yes.
Then V square is 2 mu over r, or V is equal to root 2 mu over r. That is root 2 mu over r, root of mu over r. It so happens that V circular is
Square root of mu over r.
square root of mu over r. So if you substitute this here, you're just going to get root 2 V circular.
Oh, that's what we were trying to.
That's what you're trying to
That's
do.
what we were trying to prove. Okay, understand. I see it.
So what this actually means a whole lot. What this means is, from any circular orbit, if you want to escape, so this is V escape. Because this V is associated with zero energy, this velocity is V escape. The escape velocity is always equal to root 2 times the circular velocity. So if you are in any circular orbit, if you increase the velocity by 41% or about 42%, root 2 is 1.41. So that means 1.41 times v circle. If you increase the velocity 41%, it will escape in the right direction of force. Got it? Yes, something. Huh? Oh, yeah. Okay. This is. He's here? Yes. Okay. Okay. So, alright, I think we'll stop here. Okay. The other problems are not that difficult. There are some numericals. If you want help, come and ask help or ask Tyrell, Tiffany.